I can go ahead and do it. I mean, my main thing was to get muted so we weren't getting feedback. So first thing, apologies. This wouldn't be a true academic presentation if everything went smoothly. So apologies for that. It's been a couple of years since I last did this here. Second, for those of you who don't know me, you've probably been, while you've been waiting for the 10 minutes, Googling me. I can guarantee you, if you Google the used car salesman in Detroit, that's the wrong Randy Allen. If you Google the convicted felon that's somewhere around in Texas, that ain't me. If you Google the guitar salesman, I would like that to be me, but it's not. If you got the words compiler in there, you probably got the right guy there. I mean, quick summary, I think most of you guys know me, but for the ones that don't, compiler guy for a long time, done a lot of different things around, had a lot of, been fired from a lot of jobs with a lot of really impressive titles. And instant amongst all that, one of the things I've managed to do, or the things I've managed to do, is write a book and teach a lot of courses on advanced compiler construction. For those of you who are hardware types, I'm one of the primary authors of VCS, as well as the origin of a lot of Synopsys products that came along around afterwards, as well as a builder framework on it, and writers of one of the first MATLAB compilers with fixed point. So long, boring history there, but we'll come around. In terms of this talk, this is a little, this is a typical academic talk, or at least my typical academic talk. And that it really is just sort of, it's really motivated by two things. There's looking to the past, and then there's looking to the future. Where are we, and how did we get here? The where are we actually came around when I was here. I was sitting in one of the thesis presentation defenses, and someone came around and made the statement that you had to put directives in programs to vectorize them. Since I spent my entire career actually fighting against that, I felt it might be time to have one of the old guys educate the people around. Second is sort of where we're going. What are the ideas I'm looking at? Why am I here? So this is a presentation that probably asks as many questions as it answers. It's not, it's a lot of it is looking forward, looking to new ideas. And as part of that, it's looking at where we're at. What's the basis for building all this stuff on and coming around? So major goals of the presentation really are to introduce sort of reordering transformations, the whole idea behind compilers for vector and parallel machines. And in particular, they have sort of a very different approach than sort of your typical compilers. A typical compiler takes a program the way it's written, figures its job is to translate it to machine code, and does that a very passive type of thing. The type of compilers I write, the type of compilers for vector machines, will take a program you wrote and said, well, no, you don't really know what you're doing. You really want to come around and do this. It's going to go and change the program to find more parallelism and exploit parallelism out of that. It's a much more aggressive type approach. It's necessary. And with that, it leads to two questions that you always have to ask around on that. First one is the change I want to make legal? Am I going to change the semantics of the program by making this change? Or will I break something or change something? Second one, is it profitable? Is the program going to run faster if I come around and do this, or is it going to run slower? So with that, there's a much more aggressive, much more different, it's a whole different type of thing than your typical compilers. And since not that many people get associated with reordering transformations, with vectorizing and parallelizing compilers, it tends to be a different view or approach. The looking forward part, spent a lot of time looking at AI and ML accelerators. A lot of the jobs with impressive titles I've been fired from has generally been coming in as VP of software for a startup that's building a AI accelerator. They go and spend $100 million to build a chip. They get the chip, and all of a sudden they find they can't sell it because they forgot about software. So they find someone real quick to try to come in and bail them out real quick. It's what I've been doing for the last 3 years. With that, I get to see a lot of the accelerators that are out there, sort of present what I see as the challenges around on that. and then coming around with, one of the real reasons I'm here is sort of investigating what I believe is a new approach towards compiling for these things as well as for everything. Okay, so whenever I teach a course in this stuff, very first day I get up and present this slide, which is the three mantras of vectorizing compilers. It's actually interesting watching it. I teach it at Rice, and I also tell the students when I'm starting out that I guarantee you on the final exam, the first question is going to be, what are the three mantras of vectorizing compilers? At Rice, everyone is sitting there scribbling down like madmen. And when it comes to the final exam, everyone nails absolutely right. At Berkeley, half of them sort of sit there lackluster. The other half will sort of scribble it down, and it comes around to the final. Some of them will get it right. Some of them will get it wrong. I mean, actually, the ones who are most impressive on this, just as out of this, the two guys who blew the course out of the roof was Hyun-Sup Lee, who's one of the founders of Sci5, and David Sheffield, who was his roommate. But Berkeley, it was sort of 50-50. At Stanford, everyone was too busy thinking about business ideas to even be bothered with it. So they come around. But if you master this slide, these three mantras, you are probably on a par with almost all of the vectorizing compiler experts in the world. Three things in terms of vectorizing. Number one, the order in which you execute operations can have a great impact on the efficiency of things. Not immediately obvious, but if you think about it more, it actually comes around. If you move a load closer to where it's used, you free up more registers and can come around and get more speed that way. If you're familiar with instruction scheduling and stuff like that, the order in which you come around and put it there. In vector and parallel world, it's really important because vector execution and parallel execution is very different from what you get normally. Okay, so the whole approach to this, the whole goal behind reordering transformations is we are going to create a dependence relation, such that two statements, two operations have to have their order preserved. If they have to have their order preserved, there's a dependence between them. If there is no order required or whatever, then there is no dependence. So we're going to capture all the execution orders that must be preserved in a dependence relation. Once we've got that, then what that says is we can change the order any way we want as long as we don't violate the dependence relation, and it will be correct. So the whole goal around on this is going to be building up the dependence relation, looking at the legal and profitability of order changes, and then figuring out what's the best order out of that. So this was all actually fairly, it wasn't expressed this well, but, or this precisely, but this was actually sort of all the basis of everything in the 70s and 80s. It was all sort of ideas floating around that everyone knew, but didn't really come around and have a good feel for its terms precision. The third one is actually probably the most important one. There's a nice duality to dependence. So you have a dependence when you have two operations using the same memory location in some form or fashion. So the execution, the dependence relation side of that says, if I have a dependence, I can't change the order of that. I have to be careful about the transformations I make in terms of the order. The duality of that says that if I have a dependence, I have two statements that are probably using the same data, the same memory location. So if I want to take more advantage of the memory hierarchy, then I can go around dependencies and with that find ways to improve the memory properties of things. So those are the three properties, three things. I will ask a question at the end of this as to what are the three things you need to know. So, okay, just to go through what I mentioned things. You look at the top here, there is you see the program for I equals 0, A of I equals A of I plus B of I, with the green one being the fetch around on that. So you execute that, you look at the little diagrams across of it, that's sort of the executing order. The first row, first thing you're going to do is fetch the A of I, then fetch B of I, add them, and then store them. So going down, that's what you see, A of 0, B of 0, A of 0 coming around. Way you execute that in a sequential loop is exactly in that order. You go down it, you move back up, you go down it, move back up, and over and over. And, doesn't show up in this presentation, but I'll represent that with the sort of little sequential diagram over on the right. So when you come around to vector, you're going to do things differently. Rather than fetching A, B, C, you're going to fetch all the A's first, then all the B's, add them, and then store all the C's. Very different ordering. What's the way to view it from a semantics point of view is that you're doing it simultaneously. That's actually not true in the hardware, but from a language semantics point of view, the idea is you really are doing them simultaneously. So that's the key difference and the key thing between determining statements you can do in vector and ones that you can't, because that is a different execution ordering than the sequential thing. And we'll see in a little bit, that makes a big difference, can make a big difference as to whether it's correct or not. Third one, parallel loops. The standard way of doing parallel loops is you have a bakery counter type of thing. Loop comes around, it gets free, it grabs the next iteration to do and goes and works on it. So it's a very non-deterministic, type of approach to thing. You don't know which loop's going to be doing what when. It's very indeterminate. So, first processor, two processors get free, they may fetch A0 and A3, in one cycle. Then go around, they get a cache miss or something comes around. Next cycle, a couple others come in. The one that fetches A3 is able to fetch B3, A0 as it comes around, but you get more of that. The whole idea here is that operations are going in an indeterminate order. So you don't know which things are going to be when. So, it's not a regular order, but it's one that's indeterminate, and you have to assume that you don't know when things are going to happen. Okay, so how does this relate to dependence? So if we change the example just a little bit, if you look up at the top, you'll see that where there was fetching at A of I, we're now fetching at A of I minus 1. So what that means, where you see the green arrow, is when you do the second iteration on the sequential ordering, you're actually using a value computed from the first iteration. So that fetch of A of 1 had better, in the second iteration, had better happen after the store of A of 1 in the first iteration, or it's going to get the wrong results. That's sort of the whole basis of dependence. And to give you sort of an example here, if you come around, you fill them all out. If you look at doing things vector in simultaneous semantics, you can see you'll get the wrong answer, because if you fetch all the A's first, you're not going to get the values that were computed, around it. So that's the whole basis of all this stuff around here. Just to throw in one slide for to show that there is some gravitas behind this, that there is some intellectual thing. Dependence, as I showed it there, is actually a fairly simple concept. When you come around defining it mathematically and putting it in, you are going to have two references, both to the same variable, reference to A, one of which it's a subscripted variable. So you have a multi-valued function F of all the loop induction variables that maps out into a subscript around on that. So if you have, two loops around that, the I's are loop variables, two loops that go to a single dimension array, that F of I1, I2 is going to end up going to a one value thing. You could also have two loops going to three values, it's what three subscript, two values going to three loops going to two, for instance, which is what you can get in matrix multiplication. So you've got two references, one which is subscripted by F, one which is subscripted by G, which access the same memory location. So what that requires is that the two functions are equal. You will be accessing the same memory location when the two functions are equal. So you're going to get you have the equation, multi-valued calculus type of thing, that the two equations are zero. And what you're going to do to find out whether there are dependencies or not is, does that equation have any solutions? And if it does, where are they? In other words, what are the loop values and such, where the examples are things. For instance, the one I gave previously, A of 1 and A of I minus 1. It's obvious the case that they are equal when the left I is equal to 1 and the right I is equal to 0. So there's two different sets of loops coming around on it. When you have two different sets of loop values that give the same answer, then that's when you've got something that's equal. To make it really mathematically complicated, That only happens during execution. So you're going in loops, it happens in loops. So it means it's not over Rn or the real network. It means it's over a bounded set of integers. In fact, the way we'll look at it is exactly what you have there. If you have any solutions over those discrete points, then you've got a dependence. If you don't have any solutions, then there is no dependence. For those of you who are interested mathematically, that's actually the equivalent of solving, or solving linear Diophantine equations, which has been a hard problem that's been around for a long time. So there's some mathematically interesting stuff around in this. Fortunately, focus on the first aspect of dependence, and that is that there's a dependence. What you want to prove ideally is the absence of dependence when you're looking at reordering things. It's not necessary to find the solutions. It's sufficient to prove the absence of solutions. If there are no solutions to that equation, then there are no dependencies, and you can go and work with that. So all sorts of mathematical things that you can come around to do that aren't totally accurate, but that prove the absence of solutions in that bounded region. I mean, one, for instance, if you don't have any solutions in a set of real numbers, you don't have any solutions over the set of integers. So that's one of the easier ways to go about this. Okay, coming around to the third mantra, just to give an idea of what's involved in all this. Three things that come around out of this from the three bases of that basically three ways in which you can do reuse and what it is. First one, if you create a value and then use it, you don't have to store it in memory before the reuse. You can just use it out of the register. So example of that, have a of I equals and equals a of I. You can, fetch do the a of I into a register. You can use it, and then later on down, when you can store it when necessary. It's not necessary to store it right away, and maybe not at all. Obvious one, if you're using two inputs, you only need to fetch them once if they don't change in between. And the third type, the write on write in the hardware world. If you're overwriting a value, there's no need to store the first value if it's not used in between. So that actually works out to something you can use that gets really good register use, really good use of values out of that. Okay, it wouldn't be a talk on vectorizing stuff if you didn't cover matrix multiplication. So it's going to be an example that comes around this. It's one that everyone's familiar with. It's also one that you can do very well. So you see on the left side, matrix multiply, n by n. Doing it the way almost everyone writes it that I've seen, although it is interesting. When I was digging around trying to find information on the RISC-V intrinsics, I came to a site that illustrated it using matrix multiplication. The guys wrote matrix multiplication wrong. They completely botched the writing of it. That was a bad, that was the bad news. The good news was they at least botched it both ways. They botched it with the intrinsic and the way they wrote it around afterwards. So they tested, they got the right answer, but it didn't come, they got the same answer. It didn't come around anywhere close. And it was interesting that right after that was SGEM, which they did do correctly. I don't know why they didn't compare. Anyway, matrix multiplication, in terms of the way the source code works, it's basically for each iteration of the inner loop, of the innermost loop, it's selecting one element of the product matrix, C to compute, C11. In order to do that, it's sequentially moving across the rows of A and down the columns of B to do, the dot product, albeit sequentially, to come around and get that. So, excuse me, standard way of doing things. Actually, probably the slowest way to execute matrix multiplication that's out there, but it's the way everyone does it. When you're going down the rows of A and down the columns of B, you're going to have really bad cache effects. And so that's guaranteed to be slow. So the title of this actually, was Achieving Supercomputer Performance. And didn't cover that so much at the beginning, but the term supercomputing performance is actually one that was defined by Dongarra back around 82 or 83. He wrote a small paper. It actually wound up coming around, but is basically how to achieve supercomputer performance on the Cray. And his observations were that if you just look at compiling inner loops, you don't get any significant speed up over scalar. The reason was that you spend all your time waiting for memory to come around and do it, rather than running at computer speed. If there's at CPU speed, you're running at the memory speed. Which was actually, on the history side of this, on the looking back side of things, Jack and Cleve had actually just come out with the level 1 BLAS, which for those of you that are familiar with it, level 1 does vector times vector operations as the basics fundamental around it. So dot product is one of the basic operations there. And Jack, when he was looking at LinPack and all the things that used the level 1 BLAS, found that it was not worth doing anything on the Cray around on that, because it really didn't, running this, for instance, on the Cray will not get a super significant speed up over scalar. Anyway, represented this way, what it's doing, the dot product vectorizing the inner loop does the same thing as the scalar version, but instead of fetching the things sequentially, fetches them all at once. So it will do a vector fetch of A, do a vector fetch of B, do a dot product, and then store that away. Still computing one element, but coming around and then fetching around, doing the operations simultaneously to get there. The third one, which is what Jack came up with, and the interesting thing about this, he came up with sort of the application side of things. At the same time, I got my thesis out at Rice, which was able to do this automatically, which is how he, part of how he and I got to around interacting together. But rather than, if you instead of vectorizing the inner loop, vectorize the second loop, the outermost loop, so that you're doing things. If you look at the diagram there, you'll see that what it's doing is it's computing a partial result for the first row of C. So it does that by taking the scalar A1 and multiply that by the vector B that's up there. That is 1/4 of the result you need for that. To complete the product, you then have to multiply A21 times that same vector, A31 times that vector, and A41 times that vector, and add them in, you will come around and get it. So that's actually what you see up there. If you see VR12, VR12, that is going to be a section of C that it's computing. You can actually see the section down at the bottom where it does the store, C of IV equals VR12. So it's taking a vector, zeroing it, and then going through multiplying a scalar times the vector on the right, all the 4 times to compute the product, and then storing it away outside the loop. So you look at that, no stores inside the loop. More than that, all the vector fetches, these are C semantics. So all the vector fetches are contiguous memory. That is always a good thing. Non-contiguous memory may or may not work well inside memory units, but contiguous memory is always guaranteed to work well. So the whole point of this, if you come around and do this with the inner loop vectorization, give some more details, or with the middle loop vectorization, you will see out of that, you get a very big performance improvement, and particularly one that scales up. What you find when you increase the size of N on the inner loop is after you get so big, you're blowing the caches out. So it slows down tremendously. It starts really bogging down on memory. That never happens with the one on the right. And in fact, that's what led to level 3 BLAS and that type of thing, was observation that coming around and doing things this way, getting the memory reuse was the real key, or the data reuse was the real key to getting the speed you needed. Okay. So there's no audience here, but there's one little thing that you'll notice if you look at the one on the right, which actually was produced by a compiler. I never write this stuff. You'll see it unroll the loop once. Any ideas as to why it did that? I always like it when compilers surprise me. It surprised me on this one, and I had to go back and look at it. So if you look at the three mantras, your first reply should be, well, maybe it improves the performance some. It actually doesn't. Your next one would be, well, maybe it improves the reuse some. It actually doesn't when you come around and work through it. So there's no reason you would know the answer to this. But the reason so if I were to tell you that the vector register file in this machine was made out of single ported SRAM, then those of you who are hardware guys might then start getting a clue into it. So if you were to do it without unrolling the loop, it would be vector register equals same vector register plus all this other stuff. If you have single ported SRAM, you can read it in the cycle, but you can't write it back in that cycle. So with that, it actually runs slower. You really don't want to run it into the same register because you're going to get a delay reading in and reading back out. So the compiler actually unrolls it so it can read it, write the result back into a different register and then read that back. So it's ping-ponging between the registers going back and forth. So in the abstract, I mentioned Hercules and the hare and how customers could never get the same performance as users will get inside. That is a reason for it like that. Customers almost never know that there are things like single ported SRAM or stuff in there and the little things like that. One company I worked for, which will go so nameless, would put out 512-page erratas for their chips. When you got 512 pages of errata, you got a lot wrong with your chip. Compilers can know and have to work around those. Users usually can't begin to comprehend that. So that's it. Just looking around at what it comes out of when the reason this runs so much faster. I actually did, was going to take took these, generated code, was going to run them on the on the boards around here. Had it all set up and done it, but I found that the way I use for measuring clock at Sci5 doesn't make it through behave. So it reads a register down in there. So I never could get it. So I wasn't able to actually get the final timings out, but I've got enough here to show it that it gets a very significant speed up. Left is the RISC-V code, comes around. If you look at it, it's doing a standard matrix multiplication type of thing. It has n-cubed loads and stores, and it takes n-cubed operations around and doing it, with half of the n-cubed loads being strided, which means they are probably going to be slower than contiguous vector loads good, strided ones so. One on the right, the outer loop vectorization cuts the loads in half. It's because it's doing a scalar times a vector rather than a vector times a vector. It's only, in terms of vector loads, it's only doing half as many, and all of those are guaranteed to be contiguous. So they are guaranteed to run really fast. Okay. So you're now, although somewhat farther along than I intended, you are now all experts on vectorizing compilers. You have a great job future out there if you want to come into the US and go to work for companies. There are big demands out there for it. Coming around to this, as I said, the thing that got me into this was a comment that you had to put directives in the compiler on it, and directives that compiler couldn't do it by itself. My both observation and from lots of history is that the compiler is really the only one that can do this. That we're looking at things the wrong way. That what we have to do is find out ways to make the compiler do it. I mean, the quote here, probably older than most of you, but Ronald Reagan, when he was president of the U.S., made the quote when he's coming in to try to dig out the economy, which is a very bad kind. If not us, who? If not now, when? If it's not the compiler that comes in to does it, then who does this? And the quick summary is there really isn't anyone else, anything else that come out in here. Over the last 40, 50 years, there have been many, I've seen the same approaches reincarnated over and over so many times. Use libraries for doing it, use languages for doing it, use intrinsics, use directives. And the thing is, they're not there. There's never enough to do it. The whole key, if you can get an accurate dependence graph for a program, then compiler does as good as it can do. It's always surprising. It's always good when you write a program and come around and surprise it. When Ken and I kicked off the Rice vectorizer, we spent a year writing a paper where we took this one fragment of code, analyzed it thoroughly, wrote through it, figured out exactly what we would get. And I don't know how many times we looked at it. Came around and got the first version built. Was running that piece of code through one day just to see what it did. It came out with different results than what we had predicted, which was a little upsetting. I spent about an hour analyzing it and realized that it was right and we were wrong. We'd spent a year doing all this work and had written something that was much better or much smarter than we were. It really is the case that if you get an accurate dependence graph, then compilers can do as good can be done. It's hard to get an accurate dependence graph. But if you come around and look at the other possibilities, doing things in libraries never works because first, there's always the context. If you're going to do things, particularly at 8-bit or something like that, you always have to worry about alignment issues and stuff like that. And when you're called with the general library routine, if you have to come around and figure out whether it's aligned and all that other stuff, you've wasted all the time before you've come around and done it. There's also no chance of data reuse when you're going between different calls. You've hidden information around on it. Languages, I mean, there's generally a new parallel language that comes out about every 10 years or so. They always look the same. And the whole key is it assumes that the parallelism is the problem that's defined. The real problem there is being able to get the data reuse and stuff. And the languages don't do that. The only way they can do it is that if you specify the data reuse by hand. And that's not good. Intrinsics, everyone likes coding in assembler. Plus they're not portable and, you can't make it run on one machine that way. And it really is, I mean, at the point at which you have to have the human providing all the detail rather than the computer, it's not something that you want to have. The final one, the one that sort of motivated us, directives. Directives work by removing information from the dependence graph. In other words, when you put a directive in, you say vectorize this loop, you're telling the compiler, ignore what you know about dependencies. It's okay, go ahead and vectorize this loop. So you sort of completely, and you, it's usually put in sort of very naively and, in frustration. In the first production compiler I worked with, Fortran directives, you always had the form of C dollar something around, some kind of thing to indicate it's a directive and go from there. So we had two types of directives in that one. The first one was C dollar do it. In other words, do it in vector if you want it to be vector, regardless of what it says, do it in parallel and all that type of one. Second one was C dollar do it, damn it. First one didn't work, so come around and really do it, really do it in vector. But the key thing in there is that's not providing more information. It's telling the compiler not to believe the information it's got, and that never works out. So working around to the more interesting or more looking forward part of this, to give an example of where that works around to, and moving into the AI/ML space. It's an old concept as to whether it's sort of been discarded or forgotten. Is up for things. But the best way of doing matrix multiply, which is one of the key operation, in that with it in convolutions for AMI stuff, is doing it on a systolic array. I say discarded because these things, we'll go through it a little bit more, do matrix multiplication in linear time. You have 3 dimensions in a matrix multiplication. This works by mapping 2 of the dimensions in parallelism in space, one to the left and one up and down, and the third one at a time. So you reduce the problem of doing matrix multiply to a linear type of thing. So it's really fast, which is why people always want to use it. Just in terms of the key, sort of to understand this diagram. So the C's are individual processors in this. So a systolic array is a grid. I did 4 by 4 here. 10 by 10 is sort of the most common one. But, it's a grid. Each of the processors in the grid can, in any cycle, pass data to the left, to the right, and up or down, which is what the arrows around on them. The only access to the external memory or to memory outside of this are the processors on the perimeter around the things. So all the perimeters around the outside of that can access external memory. If they want to get it, if a processor inside needs a value, you have to read it in through an outside processor and pass it in, which is where the systolic comes in. You're always pumping, systolic comes from the heart. It's diastolic and systolic. It's a pumping action. So the whole idea is you're pumping data through both up and down and left and right. So in terms of matrix multiplication, the way you do this, you have your A matrix on the left, B matrix up above, C matrix to the right. You're going to pump the B matrix down and the A matrix to the right, and give you just a few examples and you get the idea and come around on it. So in the first cycle, you read in one value from the right, from the left, and one value from the right. That's A11 and B11. You add them, and then you've actually got the beginnings of the computation for C11 there. So you can see C11 is a little bit green on the right. You've done one computation for that. All your other 15 processors are sitting there, playing with their thumbs or whatever at this point. That's one of the things in parallelism, you have to do it. So second cycle, you're going to move the A's to the right and the B's down. So you will now have you have A11 over to the right, you have B11 moving down, and you go through and you add them, and you'll start seeing the products come out to be exactly right for each of the things you want to do. In terms of computing C11, A11, B11 is the first thing you need to do. A12, B21 is the second one. So you have to time these things so they all get to the right place at the right time. You move on cycle 3, you keep moving around on that. And by the time you move all the way around and all the way through, you will have on each of the processors, out there, the matrix, which you then have to move out if you want to come around and get it out to memory. So it's a very fast way of doing it, which is why, I don't know, at least all the AI companies I've worked with almost always use this as an engine coming around on it. The problem comes in, if you look at the type, it's all great. AI companies are all run by hardware guys. So they look at the systolic array and say, wow, look how fast this runs. They then come around and the compiler guys have to come around and make it run. And the compiler guys are the ones who see all the problems around on this. So number one, if you're feeding a 10 by 10 array, you have to fetch each cycle 20 values, data values, because you've got, you got 10 coming from the left and 10 coming from the right. I mean, that's okay if those were all contiguous. So you could just do, if you loading 10 contiguous bytes in one shot is no problem, but they're not going to be contiguous. If you look at the way the values are being read there, what you need on each cycle is a wavefront through the thing. So they're guaranteed to be non-contiguous, which is what makes this a really interesting problem, because you can go around. We're now in the stage where I'm looking at things I'm looking at as to where we're going or whatever on this. Is there a way where you can rearrange the memory, order the memory so you can get these to be contiguous? Or can you develop a memory unit that will come around and be able to read these, read them the way out of it? I mean, I don't think that one's possible, but I'm not a hardware guy. But finding some way to come around and take advantage, because what you find is, it doesn't matter how fast it runs around that. You just can't feed the memory in fast enough to make it come anywhere close to that. But if you were, and probably the key part of putting this example in here, the thing you would need to be able to do in order to make this work is reorder the operations. So you had the fetches you need coming in at the right time, getting the memory reordered so that you were fetching it along the diagonals around the wavefronts coming into that. one that you have to figure out is both legal and profitable to come around and do it for matrix multiplication. The second one is you want to run other things on this. Not many things fit to it, but if you did want to run other things on it, you'd want to look at different ways of doing it. For instance, there are not many things where you want to feed through that you can feed through the internal memory. Matrix multiplication is unique because it has input dependencies along two loops, so you can feed the loops down, but not many things have that. But you also have if you look at just the perimeter units, you've actually got a fairly powerful vector unit there where you can come around and do things around that. So looking at being able to program the vector side of things and reorganizing things for that, is another alternative way of looking at this. Okay, so that's the quick thing on that. Just sort of, coming around to the third item I put around there, looking at different architectures or whatever around on this, we're coming around and doing it. The one thing you find throughout compilers and everything is that, through life in general, but compilers as well, is that the key to getting the best performance is balance. I mean, the ideal thing, if you can get whatever your processing unit is, so everything is winning, 100% of the time and running at speed, not stalling for anything, you're getting the best possible performance, that you can. That's the ideal, you're getting really bad power consumption, but you're really getting really good performance. That's the ideal thing to get. If you look at one of the places in vector units where you get that, it's chaining. In other words, when for those who don't know what chaining is, if you do a vector load and then want to start a vector operation right after that, chaining will detect when, is hardware that will check when you can do that. So after you get the first element of the vector loaded that you need on, it will then chain the first operation of the next unit and get it started already so that it runs right after it. So that you're overlapping the execution of the load and the op, or if you're doing op chaining, ops and other ops. So it actually is really effective. The hard part is that hardware is the part that has to detect that. And it actually takes a lot of smarts to figure, you can't chain everything. You can't chain an op when something's going to change around in between, or you can't chain to a load when something's going to be changing in between. So the hardware has to have a fair amount of smarts in it to come around and be able to detect that and know when not to enable chaining, when to disable it. It's really hard for hardware to get that. It just has to make it. Is there someone out there that actually does have that information? I will ask the one person in the room. Do you have any idea who that might be? The compiler. The compiler actually has, with dependence graph has exact information, if it has an exact dependence graph, it has exact information around on this.
For having a better result, so you need the dependencies of this graph dependency, but also perhaps also the kind of resources that you have in the real architecture.
You need to have the hardware turn around and gear to it well, which is what around to do it. So I mean, an alternative thing, the way I'm looking at coming around and doing this is, and I'm simplifying this in terms of the architecture. But what you have, at least in my idea, the thing is you want to have everything chained automatically. In other words, the hardware does no examination for whether there are hazards or anything. It just chains it. But you also add in new instructions. I mean, they're actually very similar to what you do in parallel memories, where you have to, when you have one processor storing to memory and you got another processor, you want to make sure they all get flushed out. This compiler has to put in instructions for those. So what you do is have the compiler add in instructions that will stall a unit, tell it not to, continue on until a certain operation is completed. So, it can do that easily by checking the last element of vector register. And, when an operation completes that, it can set a flag and it can stall and come around and do it at that point. So that you can let the hardware run free until it has a compiler come around and install on things. Just to give you one example, this is matrix multiplication again. If we were to have hardware around on this, you've got the two outer loops. You're zeroing the vector register V1. Then you're doing the inner loop, that's the Daxby. You're going to load the scalar register, which is you're going to do a load of the vector section. You're going to do the Daxby. And if you keep on flowing on those things, the thing you naturally do after that is go back and start the next, the next cycle into things. So the idea behind this is that that would go ahead and run automatically, but the compiler has to be responsible for regarding the hazards. So the hazard here is, depending on your vector length, is that if you run around to the next iteration, you're going to load into V1 again, the vector register again. So if you don't, if there's enough time to where it's going to come around and that's going to overwrite V1 while the first Daxby is still going on, that you're going to get wrong results. So the VWF there is, vector wait until until it's free, is to turn around and says, at this point, stall until that vector register is free, so you don't come around and overwrite it the next, for the next iteration. Obviously, if you're doing it like this, there's no real advantage to it, because if you do, load, vector load, Daxby wait, load, vector load, Daxby late, you're not getting anything. So the way you come around and do this is you can adjust the vector lengths. So you're doing different things. You can, unroll the loop and do more things so that you don't have to put the stalls in and you're coming around on it. So there are lots of things to explore here and lots of things to push around. But it is one, it's actually very similar to what was done in the type compiler, very first thing. The compiler there was responsible for putting weights in. And, it was more for memory synchronization. At that point, vector units never had caches. So, it just wasn't physically possible. So you had to synchronize between the integer processor and the cache and the vector unit with this direct access to memory. And the compiler was responsible for doing similar things like that.
Do you have like a kind of dynamic schedule? Because perhaps I'm completely wrong, but you have a multiple system, a multi-memory vector units, for example, to do this. How can we control all of those if you want to store because of dependencies and all those things?
Well, I mean, the compiler is, responsible, for that one, to put it concretely, that machine had two load pipes, A and B, and it had a store pipe D. And you never knew what order things were going to go out and get in. So the compiler was responsible if there was a possibility that a store pipe was coming down the D pipe that might be needed by the, that might overwrite something that was being read by the A or B pipe. The compiler issued an instruction called a woody, wait on D idle, that would stall the processor until the D pipe had gotten all the way, had completed flushing and then started up again. So it's similar to that. Okay. Actually, even with the 10-minute stall, anyway, this is things I'm looking at or considering or playing with, the looking at the future. As I said, the three mantras, I would ask it again, but I give you the answer, so I make it easy. Then the last slide. So I'm a big Christopher Nolan fan. And one of the quotes I've always liked is in Interstellar, when Matthew McConaughey is looking at having to go and dock with a spinning spaceship. And, Tar says it's not possible, to which, Chris says not McConaughey says, no, it's necessary. So if you look at sort of all the problems we talked here and the importance of the reordering transformations and stuff like that. So quote from Hennessy, Stanford compiler dude, about 10 years ago, which basically said, when we start talking about parallelism and these are truly parallel computers, it's a problem as hard as any that computer science has faced. And he would be panicked if he were coming around and facing it. His other half, the Berkeley architecture dude, has turned around and said that, 10 years ago, that basically hardware guys had thrown up a Hail Mary. They were right of ideas in terms of architecture, so they were going to parallelism and throwing up a Hail Mary, hoping that someone in the software world would come around and solve them. So, I mean, to me, this is sort of like the area to come around and really explore it. I mean, people have not pushed the possibilities of reordering transformations anywhere near to what things really are out there, or what they can be, and what's going to be necessary, around things. If you look at between heterogeneous, things like AI and stuff, it's going to take compiler smarts that gets it, not hardware smarts. I haven't seen a new piece of hardware, really new novel piece of hardware invented in 40 years. They keep recycling this. Systolic arrays were really big in 1984 in the US. The reason they were really big was because Reagan came out and said, we're going to do Star Wars. And the only way they could get performance was by doing systolic arrays. So people came around and found out that it, was totally hopeless. I've seen like 3 companies about every 10 years. They come around about every 10 years. They do systolic arrays. They go out and then they fail. So it's the TPU out there now is a systolic array, and we will see whether it succeeds or not. Anyway, an area that's really essential for computer science and stuff going forward. So presentation ended only 2 minutes around, over. Happy to take questions if I can come around and do this on Zoom. I'm not coming around and sure how to do all this. So if you have any questions, ask away. And if you don't, that's fine too.
A question.
Okay.
I'm from the hardware side.
Mhm.
What are the instructions that are missing in order to improve or maybe to detect some dependencies at runtime in order maybe to change what algorithm we are using or the way that we are computing? If there's anything that we can do, we can say co-design or hardware and compilers.
Well, I mean, you can do it in hardware, and people have done it, but the point is you have really incomplete information. I mean, you have to watch cache lines and address lines to see which ones they, at least I'm not a hardware guy. I'm a software guy. So outside of writing VCS and outside of providing the infrastructure for the 2nd generation design compiler, I know what always that pause edge clock does, but I don't know too much more than that. So with that preface, you can watch cache lines, you can watch address lines and stuff and see where they come around and detecting it. But you don't want to have to track full address. I mean, it's just too much work inside the hardware to track the exact addresses and stuff. Whereas the compiler has that all in a very, very simple form, very understandable form if it's going to do anything around on it. So that to me is sort of the whole reason there for doing it in the compiler rather than in the hardware.
Okay, thank you.
Yeah, when I went to work at Synopsys, I hired one guy who had worked for me a long time. He's a little unusual guy. He always wore this really old coat, and he'd sit around the coffee room all the time. And my boss there was Kurt Koitzer. He came up to me one time and said, you got to do something about that homeless guy that sits around in the coffee room all the time. So I'm always sitting in my office. I'm always wearing the same coat, but I'm always easy for people to come around and talk to the homeless guy there if you want to. So, any other? Sorry, go ahead. No, okay. All right. Thank you.
Just, I want to say that Randy is here. He has a lot of knowledge and compilers, and he's interested in vectorization and also in AI. Many of you are working on those topics. So I think it's great if you can go and ask questions and discussing topics, because it's the way that things will move on. So thank you, Randy.
Okay.
No questions. Okay. We have recorded session, so if you want to see it, probably we will connect. We will upload the recording to the webpage. Okay. So thank you very much.
Thank you.